Okay, so the second example they do is the light scale pan. So that means that the scales themselves have nothing else. What they're talking about is scales like you see in justice. There's balanced scales where one pan and another pan are connected. It's connected, this one scale, this side, is connected by an inextensible string, meaning there's no stretching. The force is directly transmitted from one end to another. And the pan has two masses, A and B, 400 grams and 600 grams respectively, with A being resting on B. The pans are raised vertically at an acceleration of 0.5 meters per second squared, and we need to find the tension in the string. So we start off with a sketch for our pan. We've got B is on the bottom of the list, the 2, and A is on top of it. So that's 400 grams, that's 600 grams. A, B. The pan is going to be raised using an inextensible string, so it's got a tension in it, and it's being raised with an acceleration of 0.5 meters per second squared. So let's choose a positive direction. The sensible one is to choose positive going up. Now, first of all, to find the tension in the string, we can teach, as these are all moving together, we're assuming there's no squashing or anything going on here. These two are connected by a direct force. It's almost like a rod. So there's actually a force each way on them as well, and there's a force actually each way. The weight here passes into the pan and then passes back up. But all of this we can model as a single particle with a mass of 1 kilogram being raised by a tension at an acceleration of 0.5 meters per second squared. So let's do our equation of motion. So the motion is ma, 1 kilogram multiplied by 0.5 meters per second squared. And that's moving up. Moving up with it is the tension. And against the tension is the weight of the mass, which is 1g. So acting against our tension is an extra 1g of force. So we calculate T as being 0.5 newtons plus 9.8 newtons, which gives us an overall force of 10.3 newtons. Where's my pen gone? So I've lost my pen again. And they've rounded this to 2 significant figures in their answer. Got a bit of a funny printing in their document. I don't know what they're talking about there, but that's how I would go about solving part A. Part B is then talking about what is the force exerted on B by the mass A. So we now need to look at our 2 particles as if they are connected. B on A. And similar to the other example that I did, I'm now just going to put a little connector between them so we can see between these 2. This one, the weight of that is pushing down, that one's pushing up, and we've got our 600 grams. It's B. A is the 400 grams. The forces here are each one. This one is actually the force of A on B, and that one is the force equals minus the force of B on A. Okay, so those two forces are the same, and both particles are moving together as if they are connected. So they're both moving at 0.5 meters per second squared. We don't need to know at the moment what is happening. They talk about, I think, finding the force. So our mass, if we look at, consider A, and what we've got as a particle is being pushed up, the force on B on A, holding back is our weight, and the weight of A is 0.4 g. It's being accelerated at a rate of 0.5 meters per second squared. And so we can actually now work out the reaction force, or the force I've called FB on A. So motion first. Now we're talking about a particle with a mass of 400 grams, so 0.4 kilograms. 0.4 kilograms multiplied by 0.5 meters per second squared is equal to the force FBA minus its weight. So when we calculate these, we get 0.2 newtons plus 0.4 times 9.8, because they haven't told us to use any other value. They seem to sort of mix and match sometimes. Is the force of B on A. So let's do a quick calc. So a quick calculation, so we've got 0.2 multiplied by plus 0.4 times 0.5 plus 0.4 times 9.8, and that gives me 4.12 newtons. By the way, yeah, I should have considered this as being positive. Again, you can actually check it and do what happens on B. So you could do B where you've got this force of A on B coming down, the acceleration moving up, the mass of this moving up, and it could actually work out the same. But it's easier to consider A. Part C is find out what is happening to the pan. So what's the force exerted by mass B on the pan? So now we're actually considering both of these as one particle again. And if I do the draw, so we've got the pan, we've got our system above, which is now 1 kilogram, all of that. And we're saying again, the two forces on the pan and then A and B. The force going through B must be exerted onto the pan, and that includes the force of A onto B. So this is now one system. It's now moving up 0.5 meters per second squared. So we need to know, and we're going to choose positive upwards. So the force exerted by B on the pan is negative with the force of the pan on B. And this one is the one that's easier to work on as a direction. So So let's do the force of the pan on B. Oops, let's look at the diagram. So to move this upwards, we've got a force pushing up, which is the force of the pan on B, is what leads to the motion. So let's do our equation of motion. 1 kilogram multiplied by 0.5 meters per second squared. And then do the thrust, which is FBA, F pan on B, the thing to work out. So the force pushing it up, minus the weight, because weight is pulling us down. Okay, so that's 1G. Rearrange it, so we've now got 0.5 newtons plus 9.8 newtons to equal the force of the pan on B, which is 10.3 newtons. And because of that, the force of the B exerts on the pan is the negative. Oh no, it actually asks for this on B by B. I got this the wrong way around. What they said in the question was the force of the pan on A, on B by the pan. I just worked out. I was going to flip it round to give us the force on the pan. So I got this question the wrong way around.